So, let us start this lecture with a thought process. Most of people do not lead a true life of their own, as they live to fulfill others' dream. Particularly nowadays, the market forces are, making our dreams. They are influencing our dreams. We do not have our own dreams because we do not have time to think and take a proper step. So, you people should be very careful about it. And what in our scripture says, Swadharma Nidhanam Shreya, that means you should have your own Swadharma, means characteristics, right. So, in the last lecture basically we discussed about how to handle the mixture fraction, right, or the fuel ratio, particularly when we are handling in the diffusion flame, and we define a mixture fraction. We also related that to the equivalence ratio. And I also told it is a conserved scalar which is having a lot of ramification, particularly for diffusion flame, which we will be discussing later on. And now we will be continuing how to look at these combustion reactions, right. And combustion reaction basically it evolved during the reaction, and heat can be absorbed during the reactions, right. And if it is evolved, what do we call? We call it an exothermic reaction. If it is absorbed, we call it an endothermic reaction. So, question arises, if it is the case some heat being evolved and we need to find it out during certain reactions, right, then we will have to find out heat of reactions, right. Question arises, how we will find out heat of reactions, right. Let us look at a burner which is I have shown here. 1 mole of methane is reacting with 2 moles of oxidizer. Of course, it is going to the product very well, that it will be 1 mole of carbon dioxide and 2 moles of water, right. And keep in mind that it is this fuel and oxidizer entering into this reactor or the burner at 25 degree Celsius and 0.1 megapascal. It is also reaching the 25 degree Celsius and 0.1 megapascal. It is not really 0.1 megapascal, I would suggest that it should be 1 atmospheric pressure, okay, 1 atmospheric pressure. 1 atmosphere means 101,325 Pascal, okay. And you might be wondering why I have taken this, any idea? Because see, we are talking about heat of reaction, there should be some standard state, So, therefore, I have taken that, right, because the standard state is your 25 degree Celsius and 1 atmosphere pressure, not 0.1 megapascal, okay. Are you getting? So, and of course, if the it is reacted and some heat being evolved, then heat can be transferred, that is Q, okay. Now, I need to find out how much heat is evolved, because whatever the heat is released, that is going out, that is the balance, okay. So, for this what I will have to do? How I will go about it? I will have to do basically carry out a heat balance, right. So, how I am going to do for this? Any idea? Very simple questions, right. So, what we will do? We will have to make some assumptions and we will have to apply which law? First law of thermodynamics, right. And what are the assumptions we are saying? Change in kinetic energy is 0. Change in kinetic energy is 0. Change in potential energy is also 0. And steady state, steady flow process, okay. In this example, these are assumptions, right. Okay. And there is no work done, the shaft work is 0. So, with this assumption we can find out basically, which is very easy. So, therefore, if you look at we need to invoke the first law of thermodynamics for a control volume. If you look at control volume is, this is your control volume, this dashed line, right. And in that we need to apply the first law of thermodynamics, right. This is nothing but your control volume. Of course, what I have shown is a control surface, okay, but total is control volume, fine. So, now I will have to apply the first law of thermodynamics for a control volume. What it would be? It would be dE by dt is equal to m dot, I am just writing full thing and you should keep in mind that full thing, minus this is I is the inlet, this is exit He plus Ve square divided by 2 plus the Ze, okay. This is I, plus delta Q minus delta W, right. This is 0, this is 0, and I am saying the change in kinetic energy and change in potential energy is also 0, right. And keep in mind that what we are saying, we are assuming that m dot I is equal to m dot E, that is for steady flow process, okay. What is saying? The mass is conserved, okay, continuity equation basically. And by that what you are getting? You are getting basically delta Q is nothing but, what is that? Is H E minus H I, and what is E? E is here nothing but HP product minus H reactant, okay, yes or no? And that is the thing what you are getting from this expression. H means how we are getting H? H is the enthalpy, right, mass flow rate into H, right. This will be steady flow process, so therefore it will be, you know, second will cancel it out, that is the thing you will get. So therefore Q is nothing but dH, change in enthalpy. See, that is a very simple thing you are talking about, okay. And HP minus HR, HP is basically enthalpy of product minus enthalpy of reactant. What is enthalpy of product? Is nothing but summation of NIP into HIP minus NIR HIR, and this is for the basically product side, this is your P stand for product, R is reactant. And keep in mind that these are, if all these are at 298, 0 means 1 atmospheric pressure, this is not exactly 298, 298.15 Kelvin, okay, right, exactly. Then we call this as a heat of reaction. This is your heat of reaction at STP, standard temperature and pressure. Right. This is NIR is a number of moles in the ith reactant. Reactant can be anything, like for example methane, it can be methane and oxygen, nitrogen, right. I can stand for anything, right. And similarly NIP is the number of moles of the ith product. Product means carbon dioxide, and in this example water, right. And keep in mind that we have taken only oxidizer, okay, not air. So therefore nitrogen won't come into picture. So HIR, enthalpy formation of unit mole of ith reactant, and HIP is the enthalpy formation for unit mole of ith product, and this I, as I told you, it can be depending on the participating species in the reactant and also the product. So heat of reaction basically depends on the temperature, right, isn't it? But heat of reaction at standard state will be basically at the 298.15 Kelvin. So if you look at, this is your enthalpy of the product, right, and enthalpy of reactant is higher. So therefore enthalpy of product minus enthalpy of reactant will be negative, therefore it is an exothermic reaction, and this difference is basically heat of reaction at STP. Now if you look at, I have drawn these two parallel lines, will it be parallel? Will it be? It won't be, provided if Cp is not a function of temperature, then it can be parallel. If Cp is a function of temperature, it won't be, okay. What would be? You people think about it, we will discuss little later on. Why I am not giving answer right now, because you will think, okay. Are you getting my point? So, this is basically heat of reaction at standard temperature and pressure. So, if you look at heat of reaction is basically enthalpy change due to a chemical reaction, right. It need not to be only for the our combustion reaction, it can be for any chemical reaction, okay. And generally it is reported at the standard temperature and pressure. So, heat of combustion, particularly when there is a fuel, right, and we call basically heat of combustion is nothing but heat of reaction divided by the fuel, right, and that is generally this can be heat of reaction can be positive, it can be negative. If it is exothermic, it will be negative, if it is endothermic, it will be positive by the convention, okay. But heat of combustion generally, okay, not all the time, because in some book you may find heat of combustion also negative they are giving, okay. So, generally we assume it to be positive, in our calculations we will be using as positive, right, all the time, because we take mod of heat of reaction divided by the either in the moles or in the mass of the fuel, right. So, it will be megajoule per kg, right, if it is a kg, or megajoule per mole, you know, na, right, roughly some number. What will be methane heat of combustion or any hydrocarbon, what it would be, any idea? Okay, if you do not have idea, we will see, okay, we will take an example and see. So, if you look at, if I am looking at the heat of reaction, right, evaluate or heat of combustion, because if I do not know the heat of reaction, I cannot find out heat of combustion, okay. For that I need to use heat of formation, isn't it? Without that I cannot calculate, right. So, therefore, it is very important, and keep in mind that when you talk about heat of combustion, we call it as also calorific value. When you talk about calorific value, we can say low heating value or low calorific value, high calorific value. You remember we discussed earlier, right. So, that way one has to aware about this thing. So, for this reaction 1 mole of methane is reacting with 2 moles of oxidizer or oxygen rather, reacting with giving to the product of 1 mole of carbon dioxide and 2 moles of water. And heat of reaction will be basically is NCO2, that is N moles of carbon dioxide with the heat of formation of carbon dioxide 0 corresponding to 1 atmosphere pressure, and of course this corresponds to 298.18 Kelvin, 15 Kelvin, into N moles of water into heat of formation of water minus the N moles of methane into heat of formation of methane plus N moles of oxygen into heat of formation of oxygen. That means I should know these values, right. Of course, these values how I will know? This from the table I will have to use it, or is there any other way I can get, right?
Another reaction of the solution.
Yes, that again you will have to do that, say, and number of moles of course you can get from here. In this case number of moles is 1 mole here, right, water is 2 moles, right, and methane is 1 mole, oxygen is 2 moles. So, you know this thing. So, if you know these values you can calculate very easily, right. Let us consider an example like 1 mole of methane is reacting with the certain amount of oxygen in a stoichiometric ratio. Determine the heat of combustion, consider a reactant to be 298.15 Kelvin and 1 atmospheric pressure, right. So, what you will have to do basically heat of combustion, and when you talk about heat of combustion we will be looking at both, okay. That means lower heating values or the higher heat of combustion, lower heat of combustion or higher heat of combustion. So, stoichiometric CH4 and oxygen will be, right, what it would be, CH4 plus 2 oxygen going to the CO2 plus water. Water is basically 2, and keep in mind all are in gas, we are considering as a gas, right. So, change in enthalpy, heat of reaction, if you look at, we need to find out first heat of reaction, right. Heat of reaction would be, what it would be? It will be N CO2 plus HF CO2 plus N water H water right. So, from this table for the heat of formations we can get these values, right. So, for this case what will be? This will be 1 mole of carbon dioxide. So, 1 into 394 kilojoules per mole, right, you can say, or plus NS2, this will be 2 into minus 242. This is basically corresponding to gas, right. So, minus NCH4 is 1 into 74.5 plus N, what this will be basically 2 into this will be 0, right. So, this turns out to be something 803 kilo 803.5 kilojoule. Now, heat of combustion, if you look at, I am taking mod of delta H R naught divided by the mass of fuel, right. I can also express some in terms of moles also, right. Okay, I can do that, people do report, but this is a little easier to keep in mind, also easier to use, therefore, I have used this here. 803.5 mod means it will be positive, although it is negative, this will be positive, divided by mass of fuel. How I will find it out? Molecular weight of fuel into the 1 mole. So, that will be 16. So, this happens to be 50.2, right, and this will be 10 power t minus 3, this will be kilojoule, this will be megajoule per kg, which is a very big amount of what you call energy being released. Just you burn 1 kg of methane, you will get around 50.2 megajoule. Mega means 10 power to 6 joule, it is a very huge amount. Okay. And if it is a liquid, instead of gas, right, if it is a liquid, what will happen? This CH4, this will be gas, definitely, oxygen, carbon dioxide to water, it can be liquid. Okay. This is your gas. Now, this why you are doing? Because this heating value is basically lower heating value. I have given table here, you can look at, okay, maybe I will use, this is basically lower heating value is equal to this. Now, I can use the same expression here, right. If I say this is equation 1, for that I can use. So, for this what I will have to do? I will have to use these values, right, and N will be 1 mole into same thing 394. If you look at, this is carbon dioxide is 394 kilojoule per mole, okay. This is kilojoule per mole, is a 1 mole if you take, this is minus 394 plus 2 into what I will have to do? Now I will have to do, because the liquid, so 286 for the water, right, minus this will be same, right, 1 into minus 74.5 plus 0, because 0 is like heat of formation of oxygen is not given here, but this is 0, right. That happens to be something minus 891.5 kilojoule, and heat of combustion or the higher heating values HV is equal to delta SC. I can write down heat of combustion right is equal to delta H R naught divided by MF equal to 891.5 16 into 10 power t minus 3 is equal to 55.72 megajoule per kg. If you look at, there is an increase in energy, therefore, it is known as higher heating values, right. So, if you look at, like, we can really we have learned now how to calculate the heat of combustion, heat of reaction, of course, using the heat of formations. This is the one method of calculating the heat of reaction. Now, question arises, is there any other method of heat of reactions, provided heat of formation is not there, right, or it is a new compound you have developed? How we are going to do that calculation? Because we are interested to calculate heat of combustion. So, therefore, we need to know calculate the heat of reaction. How we are going to do? We are going to discuss that in a next class. Okay. Thank you very much.